Okay, so hello everyone. I'm Scott Murray. This is security hardening with the Yocto Project. I guess jump through the agenda here. So basically, I'm going to run through what security hardening is. When I say that with respect to Yocto, some basic hardening things you can do with OpenEmbedded and Yocto Project, and then I'm going to run through some description of what's in the meta security, meta SV Linux and meta SCA layers that's useful, as well as some of the choices for updater layers. So a little bit about myself. Been using Linux for, since the early days, pretty much, not quite the beginning. I've been doing embedded Linux for almost 20 years at this point. I've been using OpenEmbedded and Yocto for probably, 7 or 8 years. I'm a principal software engineer at Consulco. We're a services company specializing in embedded Linux and open source. And if you have, a need for things in that space, there's the website there. So a few caveats. I'm not really what I would consider a security expert, even in the slightest. I was kind of interested in what's available in the ecosystem, and that kind of led to this presentation. So this run through is pretty high level and not exhaustive. And of course, your own security requirements will be dependent on your product and use cases. And the intent of this presentation is to show what's available in the ecosystem in Yocto. This is an update of a presentation I gave at Dev Day back in July. There is a few new things, but a lot of the content isn't drastically different. So what do I mean when I say security hardening? It's basically hardening in the sense that we're securing a system by reducing the attack surface, which kind of comes down to removing unnecessary software and services, any unnecessary user accounts, controlling network access potentially with like firewalling, or intrusion detection on the network or even locally, kind of removing some of the default setup that might not be needed and, increases attack surface. And then as well, updates to remove vulnerabilities in the software that's on the device and so on. Why is this, an interesting topic? Well, it's kind of comes back to everything becoming internet connected, in the last 15, 20 years. The Internet of Things is, pretty much gone from just a buzzword to, an everyday, thing that we live with now. And attackers have become a lot more aware of Linux devices. There's several groups that do regular scans of all of the IPv4 address space. Shodan.io is a kind of common one you'll see references to in news about security breaches. And customers can't be relied to not attach whatever device that they have to the internet, but just for their own convenience. So this things you might not expect to be hooked to the internet end up hooked to the internet. And of course, these days, there have been some recent-ish in the last few years attacks where universal plug and play through basically like home gateways or other firewall devices may make device services that you don't expect to show up on the internet actually end up on the internet. And so that's not something you might expect. All of a sudden you're getting, calls from reporters kind of thing. And as well, attacks may not be direct. It's sort of common now to see, denial of services attacks where they're using very large botnets, or even potentially they're using a behavior of a service exposed on your device that's exploitable to drive traffic as part of a denial of service attack. Back in July at ELC, there were several presentations on security. A couple of them mentioned this list, the Open Web Application Security Project, OWASP. They have an IoT working group that does surveys every few years of the industry and comes up with the top 10 list of the vulnerabilities. it's actually quite useful because I mean, the vulnerabilities are, nicely curated in their list, and there are, things that people are reporting that they've been attacked with. They also, because it's a web sort of focus group to begin with, they have a web application top 10 vulnerability list that's quite useful as well, if, especially now that most people have a web interface. So that's also something you might be interested in. So here's the vulnerabilities. I'm going to quickly run through them. So weak, guessable, or hard-coded passwords. This is very common when you see a lot of press these days about security issues. It tends to be, people ship with a backdoor password, or a root or an admin account with a default password, or even a password scheme that's easily guessed. And so that's very common. And it's one of those things that's actually not, in the grand scheme of things, hard to fix, but it's unfortunately become, it's the top 10 it's the top vulnerability. So insecure network services tends to be in the way that the OWASP describe it, are older things like unsecured interfaces on RSH, RLogin, FTP, things that either don't have passwords or are not encrypted. Those tended to be very common in network equipment, 10, 15 years ago. And even today, some things you buy actually have them, that you can enable them. Hopefully you're not shipping hardware today that needs things like that. Insecure ecosystem interfaces, in their description of it, they mean upstream to like the cloud. So, if you don't have SSL into your cloud, based server setup, or the passwords are somehow easily derived, people able to spoof into your interface in the cloud, that's what they kind of consider a vulnerability of that class. I'm not really going to go into detail on that. That gets into more of like application development sort of things. Lack of a secure update mechanism, which is a pretty heavily discussed topic these days. Leon's actually given a presentation after this one on some of the other options for Yocto. I'm going to cover them at the end a little bit, but he's going to provide a more comprehensive run through. Use of insecure or outdated components, which is also another pretty prevalent topic in OpenEmbedded and Yocto sort of dev days and the summits the last couple of years. I'll talk a little bit about CVE checking and things like that later. Insufficient privacy protections, more about on-device storage of user data. And this starts to get into, as well as the ecosystem interfaces, things that are more application sort of or product design specific. Insecure data transfer and storage is similar. It's, not using encryption or, SSL or TLS where you need it. Lack of device management gets more into infrastructure usage, where tracking the physical presence of devices, so what's on your network. There's interfaces that you can actually see what something's plugged in and figure out where it is and do asset tracking. There's not really a lot in open source for that I have seen, so that's kind of gets more into something you would build for your own product or commercial offerings potentially. And the last couple, insecure default settings is a very broad category, and as well as a product thing. There are some aspects of that in configuration that I'll talk about as we go through. Lack of physical hardening is, number 10 on the list, because that's it's not a software thing, and that gets into a lot more very product specific type of discussion. Okay, so we have our top 10 list, and the general concerns about hardening. What can we do with OpenEmbedded in Yocto Project? So the first thing to do is to read the fine manuals. There actually is a category in the dev manual called Making Images More Secure. It provides some high-level guidelines. It does have detailed guidance around disabling things like the debug features, adding users and passwords to have specific root user password and things like that, and a discussion of some of the security related compile flags that you can, change. Does mention using meta security and meta SC Linux. And there is useful information in the that chapter in the manual. But for the most part, it's kind of giving you a starting point that you need to go beyond. So expanding on that, kind of the things I typically start off with, I mean, you want to reduce your attack surface. So an easy starting place is to check your image manifest to see if there's stuff in your images you don't expect. And you want to try and prune that down to just the bare bones of what you actually need for your product in the images, to avoid surprises, basically. So the OE package data util tool is quite useful for finding where package files in the image are coming from. It can tell you what package actually is putting them into the image. If you have package management turned on your image, you can also use dpackage or RPM potentially, but you can use OE package data util from inside your build environment. So it's very useful. The next thing would be checking your distro features. If you're using or basing off of Pocky, like the core image base, I believe, is what starts to pull in a bunch of the distro feature enabled things. It can pull in package groups based on distro features. So one of those examples would be NFS. If you have NFS and distro features, you get a bunch of extra support for that, which maybe you do not want, because I mean, NFS can be convenient for development, but unless you're building a network, a piece of network equipment, you probably don't want NFS in a shipping product. So that's an example. And mentioned in the manual is the debug tweaks. I'll just reinforce that you don't really want debug tweaks in a shipping product because it clears the root password. And I would actually go beyond that and say that in your development, once you get past, early stages, you should probably think about not using debug tweaks in your development images and focus on, trying to test something that you're going to ship, so a more useful, password scheme. Next thing would be to review your kernel configuration. So there is a security, menu in the kernel config, which has, options there. But there's also like hardware random number generator support that's architecture specific, as well as address space randomization options those are typically architecture specific. And those, depending on your evaluation of how, sensitive your use cases are, what your security requirements are, you probably might want to turn on address space randomization. There's quite a lot to hardening a kernel configuration. I give a link here to one of the projects that sort of ships a kernel config, and they have a kernel fork basically as well with some additional patches on top of the stock kernel. But their wiki has a breakdown of why they turn on certain config options, what they're trying to do, what the options do. And that can be quite good as a starting point of learning how to, come up and configure your kernel to try and make it more secure. One thing I'll reinforce here is it's been less common, thankfully, the last few years, but it has been pretty common in embedded Linux to have config devmem enabled in the kernel. The typical use case is to access device registers from user space as a workaround for not having a device driver, or to poke a specific register for to tweak something particular behavior. It's a bit better now. They added some strictness config options about what you can do with devmem in the kernel config, but it tends to be the case that most hacks that people come up with to actually work around driver issues require turning those off, which opens things back up. So if at all possible, you should try and either fix a device driver that you need, or if you need a device driver, try and work through the community to see if there's some other way to do what you want to do, as opposed to leaving the door open with config devnet. Moving on, BSP layers can be interesting in this kernel config space. They don't always enable things you might want. So C groups, namespaces, it's pretty typical. They don't turn on much of the net filter support necessarily. Nowadays, with BPF becoming a lot more commonly used for things, you need to check to see what they're turning on and potentially enable extra things. Things like the net filter, well, actually all of those become very visible with systemd or some of the container runtimes, because they expect a lot of that to be turned on. And you'll either see weird warnings or things won't work. It's common. I think Docker run C won't even start if certain things aren't enabled. There are usually checker tools. I mean, systemd and I believe Docker have some scripts that you can run to check a def config or proc config on the target to see whether it's got what it wants. So that's one way to work towards a good configuration. But the other thing that happens is you'll find that the BSP layers will turn on a lot of kernel things that you don't want necessarily. They tend to err on enabling a lot of driver subsystems and drivers. Some BSPs are better for this than others, but it is the case that people tend to use the BSP layers, at least on the Silicon vendor side, for demoing. So they turn on a lot of stuff in the kernel configs. And so you might want to prune that down because you don't necessarily want drivers for a bunch of different USB devices that your product will never see, or you don't want to support. And less commonly used, things like odd USB device drivers and stuff tend to be problematic because bugs in them, you might never expect that someone will figure out that they can plug in a particular USB device and exploit that its driver has a bug, because you didn't think anyone would ever do that with your product. So that's where you want to prune out as much as you can. The other thing I've seen in BSP kernel configs is they may enable debug options that are problematic. There's a lot of debug options that expose things in proc that make stuff like rootkits easier to kind of make work. And there's some potential performance impact, of course, as well. There's a lot of the locking and things like that. Debug options are noticeably slower when they're on. So go through and make sure, what's on there is things you intend to have turned on. So that's the kernel. To kind of go back to the the number one, the top 10 on the top 10 list, the user and password management. These days, it's really not desirable to bake in fixed passwords, and so it's very common. And you'll see in a lot of Internet of Things devices now ship with a password printed on the device or on a card in the box, and hopefully the good products actually have it that it'll force you to put a new password in when you start using the device. But the thing that I have found is there's not really tooling or good examples for schemes like that are available for simple integration with Yocto based distros. If anyone knows of such a thing, I would be interested for a pointer. You maybe mention it on Slack later, but that's likely to be something you'll have to build yourself. One thing I'll point out is that there's a convenient library in Meta OpenEmbedded, pass WQC, QC is quality checking, and a PAM module associated with that to basically do password strength checking. And it's quite configurable. You can set rules on how strict the password should be. That can be useful for building your own password, sort of entry and generation schemes. So moving on to other things we can do out of the box, the read-only rootfs image feature is definitely worth considering. a read-only root file system makes it, non-trivially more difficult for attackers because they can't modify your files. And it's definitely an interesting thing to kind of put in your system. One of the other benefits of it that these days is starting to see more of is it's quite useful for implementing reset to factory defaults, because the commonly used schemes are using an overlay FS on top of the root to keep your local changes for configuration, and to reset, you basically just wipe the overlay FS. And there's similar schemes if you're using symlinks or volatile binds into another partition, you do the same thing, you just wipe that partition. And so this, there's kind of a win-win there, right? Because you're improving your security potentially, and also getting a win on how you implement your factory default scheme. Note that this might require some development effort. Things from outside OE core and meta OpenEmbedded might not have necessarily been vetted for working with read-only rootfs. And your locally developed applications, if your app developers are expecting to be able to just go update files in etc, that's going to need some work. Typical thought goes into whether you're going to use an overlay FS or a symlink or something. The other thing to note is combining with a Mac scheme such as SE Linux, there's work there because labeling is typically done on boot with those. So read-only rootfs kind of complicates those. So the other sort of thing from the OWASP Top 10 was the out-of-date packages. So one of the things that's available in OE core is the CVE check class. And it can be used to check for CVEs, which is, the sort of classification system for security vulnerabilities. For the most part, the documentation for that is to go look at the class in OE core. In Pocky, that would be in meta classes, CVE check BB class. Note that it uses the NVD database. So the results are data dependent and may not be complete. So that's something you have to weigh for yourself if you're going to use this tool, what other steps you do or do not to kind of evaluate your CV vulnerabilities. You will likely need to process the output that you get if you want to use it in your own maintenance or long-term support process. Basically take the generated CV manifest and ingest it into some other tooling. One thing to note there is there are CVEs for some packages that are configuration dependent. So there are CVEs in the database that, say version X of a package is vulnerable, but when you dig around, you'll see that the vulnerability is tied to a specific configuration option of a package. And some of those basically don't apply to how they're used in OpenEmbedded, or they might be tied to a particular package config in the OpenEmbedded recipe. So you need to kind of sit down and go through that. One thing I'll point out is that Steve Sackerman's been doing a lot of work in the last few months on tracking the CVEs. He's generating the output and sending it to the Yocto security list every Sunday, and putting effort into both updating some of the sort of incorrect things in the CV database and sort of pushing in patches. So the Dunfill LTS branches, the numbers have been getting a very good downward trend. So definitely something to keep an eye on, and to maybe help out if you have a chance. And also I'll make a nod to David Reyna. Did a lot of work to develop and publish the SR tool, which is an issue tracker where you can actually do your own CV issue tracking for your product. So that's something that's open source and potentially usable in your workflow. So meta security, moving on, now we're outside of what you get with OE core or just plain Pocky. Meta security is kind of the next step. It's the toolbox layer, and or Git repository it has several layers in it that have a lot of packages related to security. Armin Kuster is the maintainer. And it covers a wide range of things, from libraries for different types of encryption and hashing, security compliance tools, secure boot, system integrity and attestation, which is basically being able to validate after boot that the system is still valid, some intrusion detection, as well as runtime security scanners, and some support for mandatory access control. I'll run through that. There's some documentation about what the packages provide in the docs file that I list there. And a new thing since I presented back in July is Armin's added a meta hardening layer inside meta security. I'll give a little description of that as we go along. So what support libraries are there? The one I really like to point out is libseccomp. This provides access to the kernel's syscall filtering mechanism. And it's very recommended to use with systemd and container runtimes. You'll see a lot of sort of blog posts and stuff in the last couple of years about using seccomp to increase security inside containers or systemd nspawn configurations, basically to filter out the ability for things in the container to do certain system calls. But one thing to note is to use that even with Pocky, you need to have meta security, and you need to make sure that seccomp is in the package configs for the various things. So that one's kind of, in my mind, a must-have if you're going to use systemd or container tools like runc or Docker. So that's the big one. A couple of the other ones that are interesting are the Google Authenticator libpam, which is a PAM module for integrating with Google's multi-factor authentication setup. Pointing that out because some articles in the last year or so, I've started to see a lot more mentions of customers starting to ask for MFA support on embedded systems. Anything related to that's going to sit in a data center, not so much for IoT at home type of products, but anything like a gateway or whatever. There's starting to be discussion that to avoid certain types of attacks, multi-factor authentication starts to become very appealing, and people are getting used to the idea because it's a lot easier to set up now with Google tools. So that's something that's maybe down the road you might start to think about needing. There's some hashing and compression libraries that aren't in Meta OpenEmbedded that might be useful depending on what you're going to do in your product. So there's a meta security compliance layer. It's actually a sub layer inside the repo. So Linus and OpenSCAP are the kind of big tools that are in that layer. I'm not going to go into a huge amount of detail on Linus. I have never used these tools. I kind of did some research on them. But OpenSCAP is interesting. Armin's done a lot of work to do some integration work in the layer for it. So SCAP is a security content automation protocol. And it's basically a lot around standardizing naming for basically working with tools and databases. So NIST have a database with a lot of standardized package names to allow tracking whether things are vulnerable or not. And Armin's done some work on actually kind of hooking that up. And OWASP and OWASP daemon tools that are buildable with the recipes in the layer basically allow you to go check NIST from on target, to check the database to see if any of the installed software is vulnerable. I think that kind of tooling gets into the whether you'll need that or not. It's not necessarily the case for a lot of typical embedded products that's a use case you might need. But even then, in a QA role, you could imagine building an image that you maybe automate testing to make sure, on top of running the CVE check, build some automated tooling around this. But if you're in an infrastructure environment, maybe you absolutely need OpenSCAP. So it's available. I'm sure Armin could explain that in a lot more detail on Slack if you have any questions. So moving on, we have secure boot. in integrity checking. There's TPM support in the Meta TPM layer. The trusted platform basically is, this secure enclave for secrets. The x86 secure boot is basically all based around using TPM. So there's some options in here. There's basically machine features to enable the support, turns on the drivers in Linux Yocto. There's some sample images to build the bits in to use it. And it gives you a starting point using beyond just secure boot, but actually doing runtime integrity checking and key storage and stuff. That's going to be custom development. And that's the case for a lot of these integrity-based tools. Is once you get outside of basic secure boot, it starts to be custom. For ARM, as opposed to x86, usually secure boot is vendor specific in some way. It's improving somewhat with trusted firmware and Opti, but it's usually, you'll find that you'll have to actually go to your vendor BSP layer to check for, what they have in there, and, whether they've got the hooks to do anything that, SOC specific in it. The trusted firmware now is sort of started a rationalization. There used to be most SOC vendors had their own forks in their BSP layer, but work has started this year and sort of integrating into us, or working towards using a single sort of upstream recipe in Meta ARM. I know TI have moved to that. I'm not sure who else really has jumped on it yet. But that's hopefully we'll see that more of that, so you don't have to worry about, different versions of these things in different layers. But of course, key storage and image encryption, things like that going beyond just the basics is going to, probably be custom integration work on your part. So the next sort of step beyond that is the meta integrity layer that's in meta security. The integrity measurement architecture and extended verification module recipes in there, those are features that have been in the Linux kernel for quite a long time at this point. And they basically do secure, which is what they mean by measured, boot up into user space. And so this is more basically building the kernel with keys and checking signatures against files in the file system. And because it's secure, the kernel's been securely booted, it's basically you're measuring that the file system is still valid. And as well, you can kind of leverage that to do runtime checking. So you can actually, trigger a check that says everything in the system is still actually valid, and attest to that to some remote query. This kind of is like things like the OpenSCAP, is whether you need to build this. There's people in infrastructure sort of products, power, and water and things like that, things that are highly, security conscious these days. There are companies building these types of things on top of Yocto distros, but it is work. It's not a trivial thing to actually do in practice. But meta integrity does have the tools and some sample image recipes. Another option is this link onto GitHub. There's a layer called Meta Secure Core, has an alternate implementation than what's in meta integrity, and it's got a bunch of documentation. It's kind of its own thing. If you think you need this, I would suggest going and looking at Meta Secure Core and reading through the docs and figuring it out, because it's quite involved. So that's IMA and EVM, that type of integrity checking. The newer thing that people have moved to, and this, we're starting to see a lot more usage of, is a DM-Verity. And so support for DM-Verity images have recently been added, I think back in late last year, early this year, to Meta Security. And so the difference is the integrity measurements happening at a block device block level, which is a lot simpler to kind of make work. Comes out of Android. Google developed this for Android. So in the layer, there's a class for basically generating images that have the per block hash information attached. And this is, sample configuration for actually doing a test image on a BeagleBone Black. But actually integrating what's in the meta security for DM-Verity with your secure boot, that's going to take some extra work on your part. So that's integrity covered. Intrusion detection. The classic tool is Tripwire. Probably anyone who's done any security stuff on Linux has heard of Tripwire. It's been around for a long time. So there's recipes for that, and Samhain, which basically both of those are runtime security checks. And Suricata is a thing we started to see recently. Tends to be network equipment vendors are using Suricata because it's a basically traffic inspection tool. And so you basically build that into your image and have it look at incoming traffic to look for patterns. So there's recipes to build those. Those are, maybe not necessarily things that a small embedded device would be worried about, but you can build these types of things with meta security, and if you need them. The next sort of thing is runtime scanners for configuration checking. So Linus is a tool that does some of that, which I mentioned Linus a little bit earlier. But there are other recipes for tools in here. There's Buck Security, Check Security, and Check Rootkit. Those are things for doing simple runtime checks. And then the next thing up from there is Bastille, which has been around for a long time, but unfortunately, development seems to have stopped. You can still build it, but it would probably be, you'd need to put some thought into how useful it is for you at this point. Some of these tools there's a lot of documentation from server Linux community, so that probably would be where you go to kind of evaluate whether you need them and what you would use them for. Get into mandatory access control. So Meta Security has recipes for AppArmor and SMAC and Tomoyo. SE Linux support is in Meta SE Linux. So there's some notes about these Mac systems. So AppArmor,
but 1 second, I'm lost in the slide.
Oh, so sorry, that's 26. Sorry.
Yeah, I knew it was wrong. Sorry, go ahead.
No worries. So the application profiles that you get in a default build of what's in Meta Security for AppArmor, there's not a lot of profiles, and that's AppArmor's configuration is kind of per app. So if you were going to use AppArmor, you'd probably need to start looking at Ubuntu or Debian for other profiles for applications. Similarly, SMAC, the default policies are pretty sparse, and you'd probably have to do development. The issue with SMAC in that respect is the user base is quite small at this point. It basically ties in that Samsung do, and automotive grade Linux that I work on is also uses SMAC. But using it in your own product, I think you're going to have to do some development, and finding support for that might be harder to find than SE Linux. So it's kind of the case I would sort of recommend looking at SE Linux or AppArmor first, as opposed to SMAC. The meta hardening layer that I mentioned as a recent addition, it's went in for GateScarth, the new 3.2 release that's coming. It has some BP appends basically to tighten up configurations on things. Basically make the default UMask stricter, remove write permissions from users and groups, blocks sudo as root, cuts out some of the default SSH configuration that's not particularly secure. But it's kind of a work in progress. Armin started it recently, and it's kind of a starting point. And you're going to want to review the changes that it makes and maybe add your own. And there's a README file there. I suspect Armin would be open to suggestions as to extra things that could go into this layer. So moving on, I am running out of time again, same as the last time. So Meta SE Linux is where you would get your SE Linux support. Same as like the integrity stuff is recipes and package groups and sample images. The reference policy is basically what you get with the with the default build there, and there's some choices on what policies you're going to pull in. But typically targeted is what you'll see on desktop Linux is probably a good starting point. But the thing about SE-Linux is that, as people have always said since it kind of was created, is configuring it is very challenging. Policy development is involved. And so you're going to want to invest time into that if you want to actually use Mac, SE-Linux. But why would you consider that? I mean, it has been the case that people thought this was too much work. And so when people have used Mac systems, they tend to use AppArmor and SMAC because they're easier to configure. And that's why Tizen, uses SMAC and AGL. But SE-Linux is becoming, I think, more interesting because now that everyone wants to do containers on, edge devices and IoT devices, basically the container runtimes now all kind of assume that you're going to have SE-Linux. And, all the big server distros and, the big RHEL and CentOS, community, they use it. And it's just there for them because it's integrated into libvirt. And the sort of benefit of it you'll see is, I mean, last year there was a kind of well-publicized CVE of a container escape out of Docker and, run C-based runtimes that was blocked if you had SE-Linux enabled. So kind of, I think at this point, it starts to maybe require some thought as to maybe for these simple container hosting distros that you can build, think about trying to actually make SE-Linux work with them. So Meta SCA, I mentioned way back in my agenda, and it was mentioned, I think, earlier as part of Jens Simone's talk about the static code analysis. It's a collection of tools that Conrad Weinman keeps in a layer. Has some static analysis tools for C, C++, Python, and Go, and a few other things, as well as a whole bunch of linter tools as well. There's classes to enable those for package or per image scanning. And in Jens Simone's talk, he talked about the Meta code scanner. That's another option for C and C++. Meta SCA is good because it has so many things in there you can pick through and turn on what you want. And he's actively maintaining it, so it's pretty up to date. I'm getting low on time. I will just quickly kind of give a couple of quick updates because Leon's going to talk about the updaters in his presentation next. So there are several tools, and this comes back to the, a secure update mechanism as one of the top 10 vulnerabilities. There are layers for SW Update, Mender, Rock, and Actualizer. There are a few other tools, Intel's Meta SWFD, and you can build your own with like straight OS tree. There's support for that in some layers. I'm not going to go into a lot of details on these now since I'm running out of time, but the slides kind of have this run through. But one thing I'll point out, a difference from my presentation in July on this is Meta Updater, the actualizer client and that it provides basically would normally, if you were going to buy commercial support, you would use here, have a thing they call the OTA Connect platform. Recently, they've indicated that they've decided to sunset that, and it will go end of life in 2025. So if you were interested in Meta Updater, because of the ones I mentioned in the slide deck here, it's the OS tree based one. Note that you may have to actually, think ahead about what you're going to use for your server side, because here are no longer going to be an option after 2025. So just to sum up, this was a non-exhaustive survey and kind of run through some of the options that you get from layers that are available on top of Pocky or OE Core. I've definitely skipped things in Meta Security. There's definitely other recipes in there that might be useful. If there's something in particular, I mean, I didn't really discuss network or firewall tools because those tend to be, a little more specific to product, and I'm not an expert on those by any stretch of the imagination. But if there's something in particular, maybe drop me a note, and if I do present this again, I can add some stuff. And my contact info is there. I'm on the OE and Yocto channels if you want to drop me a note. And I'll be on Slack after this to take any questions. Thank you very much.